Hello everybody and welcome to chapter 6.3. Today we're going to be discussing transformation of logarithmic functions. So essentially, all we're going to do is again understand the different transformations that affect the function, and then we're going to learn how to apply those transformations to actually graph every type of logarithmic function. So let's get started. When it comes to understanding the transformations, the most important thing you have to do is understand that these transformations are the exact same ones we've been doing for all the other functions. So once again, we're dealing with our c, d, a, and k values. Those values still mean the exact same thing. So for example, when we see a plus c in log of x plus c, that means that we're translating something vertically. So if c is greater than 0, we're translating c units up. If c is less than 0, we're translating c units down. The same thing goes for d. Again, if we see a d value, that means we are horizontally translating something. So if d is greater than 0, we're moving d units to the right. If d is less than 0, we're moving d units to the left. Our a value, surprise, is still the same thing. We're still talking about vertical stretches or compresses. So if the absolute value of a, and it's important that it's the absolute value, is greater than 1, then we are stretching vertically. If the absolute value of a is less than 1, then we're compressing vertically by a factor of the absolute value of a. And if a itself is just less than 0, so it has a negative in front of it, that means we're reflecting in the x-axis. Lastly, our k value, by no surprise, is talking about our horizontal stretches and compresses. So essentially, again, if the absolute value of k is greater than 1, then we're compressing horizontally by a factor of the absolute value of 1 over k. The same thing goes for when k is less than 1. We're now stretching horizontally by a factor of 1 over k, or the absolute value of that. For this, we have to acknowledge that k cannot equal to 0, because this value here would then make no sense. Lastly, if k is less than 0, we're reflecting in the y-axis. I will do now a small presentation on Desmos on how these values actually interact with one another, so we can understand these concepts even more. Okay. So here is our little graph. First of all, these ones need to be hidden. Sorry about that. So here is the graph of log of x. Again, log of x means that we are dealing with the base of 10. So our key points would be at 1, 0, at 10, 1, and at 0.1, negative 1. Again, it's just dealing with the powers of 10. So let's look at what this c value does. Oh, wow, it moved us down. What a surprise. As you can see, when we change the c value from positive to negative, it simply moves this function up or down, respectively. With our d value, it's moving it left or right. Again, if it's positive, it's moving to the right. If it's negative, it's moving to the left. We've done this a million times before, so it shouldn't be surprising. Our a value originally starts at 1, and when it is 1, there is no change in the graphs. So a log of x when a is equals to 1 is the same as log of x, as we can see here. They're identical. However, if we change a to be positive and greater than 1, the function is now vertically stretched. So for example, if we made this 6, before we had 0, 1, 0. So 0 times 6 is still 0. But we had 10 and 1. So now that 1 was multiplied by 6, so we should have a point of 6, which is correct. Then at 0.1 we had -1. So now at 0.1 we should have -6, and we do have that. So with that information, we know how to apply our A factor now. Again, if it is between 0 and 1, it is vertically compressed. So if at 0.5, our A value here stays, or Y value is still 0, but at 10, it should be 0.5, which is correct. Over here, it should be 1/2 of whatever was here, which was -1, so 1/2 of -1 should be around or exactly -0.5. Again, if we let this play, we can see that when it turns negative, we get flipped in the x-axis. Again, let's look at that. Bam, and it got flipped. Lastly, we're dealing with our k value. So our k is responsible for any horizontal stretches or compressions we may have. If it's 1, we don't have a change. It looks identical to our first graph of log of x. If it is greater than 1, it is horizontally compressed. As you can see here, let's make it 5, for example. 5 would mean we have a compression factor of 0.2. So again, we used to be at 1, this should be 0.2. We used to be at 10, so now we take 1/5 of 10, which should be 2. So we should be at 1 when the function is at 2, which is correct. So again, you're just gonna multiply the respected value by whatever factor you have. So if we were between 0 and 1, so 0.5, our stretch factor now is 2. So we were at 1, now we are at 2. We were at 10, now we're all the way at 20. Again, it's just comes with practice, these understandings of these concepts, but it is rather simple either way. Again, if we let this play, see, we get to flipping it on the y-axis when it is negative. Again, that's just super simple to remember. If we have -k value, flipping it on the y-axis. Combining them all together, we get this following function over here. So if we let them all play at once, we get the transformations that may look something like this. These are all possible different values or graphs that you can achieve. Again, we will figure out how to do all of these together, so do not worry, it is not as complicated as it may seem. Hopefully you like that little presentation, but now we need to move on to actually discussing how to graph these logarithmic functions. So again, you must remember that when we're graphing something with various transformations, it's so much easier to divide them into different steps. So our first step should be to always identify that we have the correct form. The trick here is always within these brackets. So sometimes you might have a value of like 0.5x minus 2. You should understand that you have to factor out the 0.5. That is our k value. When we factor out 0.5 from 2, we will get a different d value than what it would have seemed like. That is why it's super important you get to this form here. Once you have the correct form, or once you check you have the correct form, you can apply your horizontal and or vertical stretches and compressions. Also, our next step would be to apply your reflections. These steps can be changed in order. So for example, you could apply your reflections first and then do all of your horizontal vertical stretches or compressions later. However, the most important part is that you leave the horizontal and vertical translations for last. You have to do them last as they simply move your function up or down. If you don't do them last, you could easily mess up on the rest of the transformations. Once you understand these steps, you need to understand what functions we're actually going to be dealing with. Since we've discussed that log is the inverse of the exponential function, you could be dealing with, for example, log of base 2 or log of base 17. However, in this chapter, we're only dealing with the transformation of the common logarithm, so to the base of 10. Once we know that it's only to the base of 10, we can easily remember its key points. So for example, you'll always have an x-intercept of 1. So your key value will be at 1, 0. Next, you have to remember two other key points, which would be 1 and 10, because 10 to the power of 1 is 10, and then 10 to the power of 0.1 is equals to -1. So these are the values you must remember. Lastly, it is super important that you always label your vertical asymptote. Your vertical asymptote will be at y is equals to 0. Lastly, using all this information we just discussed, we could now graph the function that we have here as an example. This is probably going to be the most difficult function you can graph in this chapter, which is why I feel like it would be a beautiful example for us to color together. Okay, so I've copied down the question over here and created this beautiful little graph. As you can see, our x-axis is pretty long, and so is our y-axis. The reason for that is that you can immediately identify the 1/3 over here, which would mean we're horizontally stretching and vertically stretching as well, which would mean we should have a pretty big x and y axis. So what I would like to do first is draw our base function. Our base function had an asymptote at x is equals to 0. There you go. And then our other function would be at, our other points would be at 1, 0, at 10, 1, and at 0.1, 1, so like really close to over here. This might seem a little bit difficult to draw, but I will show you on Destos just how close these lines get, and honestly, doing them by hand is nearly impossible for them to be perfect. So this function over here is log of x, or y is equals to log of x. This is our base function. Next, we could identify our parameters. So a is equals to 2 or -2, k is equals to 1/3, g is equals to -2, and c is equals to -5. Immediately, we know that there's a reflection in the x-axis because of the -2. This we would horizontally stretch by factor 1/k, which is equals to 3. That is all we need to know. So let's start with the negative. That's what I personally like to do. So this point stays the same. This got reflected. And this point over here got reflected as well. So now our function is something of the following form. There you go. So this is y is equals to -log of x. Next, we can apply our other transformations. So what are our other transformations? Well, our vertical and horizontal stretches. So let's analyze the vertical stretches first. Every point we used to have now was vertically stretched by a factor of 2. So here we had 1, 0. So 0 times 2 is still 0. However, here we had 10, -1. So -1 times 2 is -2. Here we had 0.1 and 1, so now we have 0.1 and 2 as our points. From these points, we can apply our horizontal stretches, which were by the factor of 3. So now we're looking at our x values. So 1 times 3 is 3, so now our point is actually over here. This used to be 10 and -2. 10 times 3 is 30, so we're at 30 and -2. 0.1 times 3 is 0.3, so we're around over here now. As you can see, this point barely moves, which is why it's super difficult to graph. However, now that we have our 3 new points, we can graph our second intermediate function. Again, this is super long, so I really cannot provide like a solid, beautiful line for you guys. but this is the best I can do. Oh, sorry, that's not good. There you go, something like this. I'm gonna try to make this fit more into the x-axis or onto the x. So something like that. There you go. That's better. So this is the graph of y is equals to our a value, so -2 log of our k times x value, so 1 over 3x. Lastly, we can apply our c and d values, which would conclude our graphing process. So how do we do that? Well, we need to identify these points now. So this is 30, -2. This is 10, -2. Oh, sorry, this is... Give me a second. This is 10, -2, which we already moved, so it could get out, right? That's not part of what we have to graph anymore. Lastly, this was 3. This is 3 and 0. And this over here was like what, 0.3 and 2. These now get our D and C values treatments. So first of all, we moved everything 2 units to the left. So 30 became 28, 3 became 1 again, and then 0.3 became 1.7, or -1.7. So somewhere over here. Then our C values moved everything downward. So -2 became -7. There you go. This point became this point. This point got moved down to -5, and this point from 2 went to -3. So these 3 points, we actually have a new asymptote, right? Because of our D value. So our new asymptote should be at -2. The way we can find the asymptote is by simply evaluating the value for which would make the brackets here equal to 0. So we write x minus 2 or x plus 2 is equals to 0. Therefore x is equals to -2. That is our restriction. Make sure you state your restrictions, people. X cannot equal to -2. There you go. But this is equals to -2. Now, let's graph our final function. We have our points. So we're putting this through here. Oh, sorry, that's too early for me to go down. There you go. This point. Then we go through here. And then we're going through that point over there, which is nearly impossible to do. I will try my best though. Oh, nope, it just disappeared. I'm so sad. Let's see if we can redo that graph. There you go. Oh, yeah, this is nearly impossible. I'm so sorry, guys. Again, I'm gonna show you these graphs on Desmos, so don't worry about them being way too untidy, because I will explain everything on a wonderful Desmos generated graph. Now, let's label our answer or our final graph. And we have completed our sketching process. So we went from this function over here, the red one, all the way to this gray one. As you can see, there's quite a bit of change that has occurred, but it wasn't anything difficult. Making those 2 intermediate graphs really helps us apply all the transformations we need. Now let's look whether or not we did this correctly using Desmos. Okay, so this looks a little bit confusing, but this is the graph we made. I know it's so amazing. We're so happy. But here is the Desmos made one. This used to have our function here. So I'm gonna delete all these. These are not needed anymore. We can substitute our values in. So we had -5. We have D is equals to -2. A is equals to -2, and then K is equals to 1 divided by 3. Or sorry, 1 divided by 3. So our function that Desmos has generated is this one over here. Let's see if that's correct. So our key points became 1 and -5. Let's try to get 1 and -5. That's perfect. Our next point was at 28 and -7. 28 and -7. Perfect. Lastly, we had a point at -3 and like 0.7. So let's see what -3 approaches. So -3 is around, come on, it's -3 is -1.7. So perfect, we got those correct. As you can see, even though our graphs weren't the prettiest, we have conveyed all of the key information well enough to graph the same exact function. If we really want to, we could also graph our intermediate graphs as well as our log function, and they all align. As you can see here, the colors, I could actually change the colors so they look the same. So red, then we had our blue, this used to be blue, this was green, and this is our final function. So as you can see, they are the same things. They have the same values, but now this one's just more organized, of course, since it is in Desmos, and this one was our favorite child. Now let's talk about the homework. As you can see, today's lesson was also a little bit on the shorter side, but genuinely, this whole entire chapter is covering everything we've learned before, just with a new type of function. Nothing is really difficult and too much to explain. For that reason, I only assigned 5 questions. They're genuinely testing if you can do the exact same procedure we just did, just on different values. Again, I hope you have enjoyed today's lesson. It's pretty easy so far, but if you have any questions or just unsure, please leave a comment down below and I'll try my best to answer it, or for example make a video on it. But if you're all good with the content, next class will be covering 6.4, which is getting more into algebraic type of questions. So I can't wait to show you that. Again, thank you for listening, and I'll hope you see you next time. Bye bye!